Intel 18A gets head start on TSMC N2 with Fab 52 ramp. Intel announced this week that its Panther Lake processors have entered volume production at Fab 52 using the company's 18A node, which is touted as the first 2nm class process to achieve high-volume manufacturing. This milestone gives Intel a slight timing advantage over rival foundries like TSMC, with its N2 node, and Samsung with its SF2 node. However, being first does not guarantee a lasting lead. Customers, partners, and investors will focus on Intel's ability to maintain parametric yields, control manufacturing costs per unit, and expand 18A beyond limited compute tiles. While Intel has shared improvements in defect density and early functional test results, comprehensive parametric yield metrics that demonstrate consistent achievement of power, performance, and frequency targets remain undisclosed. Initial shipments and early ramp figures will determine whether this production start is symbolic or substantive for Intel's manufacturing revival. At the transistor level, 18A node introduces two major innovations: ribbon-fit gate all-around transistors and power via backside power delivery. Ribbon-fit replaces vertical FinFET fins with thin horizontal silicon ribbons wrapped by gate material, enhancing electrostatic control, reducing leakage, and allowing shorter gate lengths. Intel reports approximately 5 to 10% shorter gate lengths when transitioning from FinFET to ribbon-fit on 18A and claims over 20% reduction in per transistor power. Power via relocates the power network to the wafer's backside, freeing up front side metal for signal routing, shortening power paths, and reducing voltage drop at high switching rates. Together, these changes lower switching energy and provide designers with more flexibility to increase frequencies or reduce power consumption in notebooks and other mobile designs. The impact of these transistors and power improvements on finished products depends on packaging and tile-level design. Panther Lake employs Foveros S, a 2.5D pack aging approach with fine-pitch interconnects around 36 micrometers to integrate compute, graphics, and platform tiles into a unified system on a chip. This modular method allows Intel to manufacture each tile on the process node best suited to its function, improving functional yields and reducing the risks associated with large monolithic dies. In Panther Lake, the compute tile is made on Intel 18A, a 12 GPU tile is produced on TSMC N3E, a smaller force tile is built on Intel 3, and the platform controller runs on TSMC N6. This mix of nodes and tiles gives Intel the flexibility to optimize performance, yield, and time to market while allowing independent iteration of graphics, compute, and I/O subsystems. Strategically, Panther Lake and 18A provide Intel with a visible engineering proof point as the company seeks to attract foundry customers and restore manufacturing credibility. However, commercial success will depend on cost, yield stability, and ecosystem support as much as technical innovation. Published high-density figures favor TSMC's N2 in terms of raw transistors per square millimeter, but Intel argues that power via increases effective usable area for practical designs and that ribbon-fit combined with backside power delivers noticeable efficiency gains in real workloads. Backside power delivery also adds process complexity and cost, so Intel must demonstrate that these trade-offs are beneficial at scale and across product families.